Let's take a look at atomic mass and understand how we get the numbers that we get for mass on the periodic table. So when we look at atomic mass, we are comparing things to carbon-12. Carbon-12 is incredibly abundant and there's tons of it and it's super stable. So we're looking at the average relative mass of the isotopes of an element compared to carbon-12, which we've defined as exactly 12 AMU. What is AMU? It's atomic mass unit, which sometimes we also abbreviate as just a U. We like abbreviations. Less writing. So an atomic mass unit is 1/12 the mass of that carbon-12 atom. And that's where that 1.6606 times 10 to the negative 24th grams comes from. Okay, so when I look at two elements like carbon and technetium. So carbon, I've got that 12.01. So that's not exactly 12. And that's because there's different isotopes of carbon that are each going to have a weight. And that weight is going to contribute to the overall mass of a given sample of carbon. Now, technetium, notice that that mass number is written in parentheses. So we have some elements that are just radioactive. They're not stable. And so the mass number there is, instead of having an average weight of the known stable isotopes, we just have the mass of the radioactive isotope that we were able to isolate. There's a few naturally occurring elements like this, but a good portion of the elements like this are ones that have been created in a particle accelerator by smashing things together. They usually only exist for a very brief fraction of a second. Okay, so we cannot tell the number of isotopes based on anything on the periodic table. It's just a matter of experimental work. So if I look at chlorine, so chlorine has an average mass of this 35.45, okay? So chlorine has two known isotopes, chlorine 35 and chlorine 37. Now, you may have learned averages where you add up everything and divide by the total number. So if I took 35 and I took 37 and I added those together and I divided by 2, because there's two of them, I would get 36. But I don't have 36 as my mass of chlorine. I have 35.45 because 75.76% of chlorine has a weight of 35, and only 24.24% of chlorine has a weight of 37. So in a sample of chlorine, I have a lot more atoms that weigh 35 than I do 37. And so that's why we have to take the percent abundance and do a weighted average, because each isotope, there's a certain amount of it, and that contributes that portion and that portion and that portion. So we get these weighted averages based on the percent abundance, because there's more 35 than there is 37. And so my mass is closer to 35 because more of the particles only weigh 35. Only a few of them weigh 37. And those few that weigh 37 is what drives the mass up over 35. Magnesium has 3 known stable isotopes, so magnesium 24, 25, and 26. Our average weight of magnesium is 24.31 because the majority of magnesium is actually magnesium 24, 78.7% of it. Okay, and so again, we get that, average relative mass compared to carbon. Okay, so how do we do this? So if I look at silicon, I have 3 isotopes here. Okay, I have silicon 28, 29, and 30. I have a mass, a percent abundance, and then I have this portion contributed. So basically what we're doing is we take the mass, multiply it by the decimal form of the percent abundance, and we get the portion contributed. When I get each of the portions contributed, I can add them all together. Or I can just set up, one thing. So the way I would set this up is I would have, let me change the color of this. There we go. Okay, so my silicon 28, I have 27.97693. I'm going to multiply that by the percent abundance in decimal form. This is the place where I see the most errors on these calculations, is you have to convert the percent to decimal. So 92.23% gives me a decimal of 0.9223. So I'm just dividing it by 100. Okay. Okay, then I bracket that off. Add to that my next one. 28.97649. Okay, and then 2.67 divided by 100 gives me 0.0267. So there's my decimal form. And then add to that the last one, 29.97377 multiplied by 0.0310. And that gives me this 28.0855. Now, most periodic tables round the masses off to 4, maybe 5 significant figures. We actually know these masses out a lot further. As you can see here, I've got, 7 significant figures in each of my masses. So we do know these numbers really, really well. We've got really good detection techniques, but we usually just mount them off because we're not going to print a periodic table with a zillion significant figures per every little box. Okay, so let's take a look at another one. Okay, so here's neon. Okay, so again, we take the mass, and then my abundance put into decimal form. Okay. Okay, now 0.27% you might think it's already decimal, but it is still a percent. So 0.27 divided by 100 gives me 0.0027. Don't forget to convert to a decimal form. Okay, and my last one. Okay, and so when I do this, I get 20.1771, which will round to 20.18 to keep the same number of significant figures as in the masses given there. Now, if I want to check my work, I can look on the periodic table and I can go to neon. Oh, the mass given on the periodic table for neon is 20.18. We get that atomic mass units. Okay, and let's do one more. Hey, silver 107, silver 109. So if I took a simple average of these, I'd get 108. But my percent abundance, while close to 50-50, isn't quite. It's 51.84% silver 107. So this tells me that when I calculate this, I should have an average weighted mass slightly closer to 107 than I have to 109, because a little bit more of this weighs 107 than 109. So let's see. Okay, and then 0.5184, and then I get my 108.905, and 0.4816, comes out to 107.868, which rounds to 107.9. So, yeah, it's close to 108 because it's a close to 50-50 distribution, but it's not quite. So I get that 107.9. So just a little closer to 107 than it is to 109. So that's how we get our weighted averages for those masses. This is also how I calculate your grades. So in the syllabus, you saw this is 40% and this is 10%. And so your grades get this weighted average applied to it in order to calculate your overall grade. But a lot of professors do that.